Welcome back, everybody, for another deep dive. And today, we're going to be looking at something that sounds like it's straight out of science fiction.
Oh, yeah.
Fully autonomous programming.
Wow.
We're talking AI that can write and fix code completely on its own. And our source for this deep dive is a brand new research paper from February 2025,
Okay.
detailing a system called SER. It's pronounced like the Norse magic cedar.
Oh, very cool.
So, get that little bit of mystery in there.
Yeah.
Now, the researchers behind SER built it using multiple AI agents that work together.
Right.
Kind of like a team of specialized programmers.
Okay.
But before we get into the how,
Yeah.
let's talk about the why.
Sure.
Why is fully autonomous programming such a potentially huge deal?
I think, one way to think about this is to imagine the possibilities if AI could handle all of the tedious, error-prone parts of coding.
Yeah.
Right? Like, we could build software faster, more efficiently, and with potentially fewer bugs.
Fewer bugs, that would be amazing.
Right. Think about all those late nights you've pulled trying to squash, one particularly nasty bug.
Ugh. Yeah.
What if AI could just take care of that for you?
Sign me up.
Right.
But I'm guessing it's not quite that simple yet.
You're right. It's not that simple. And one of the big challenges with AI code generation has been what researchers call near-miss syndrome.
The near-miss syndrome.
Yeah. So you get code that looks perfect,
Yeah.
to the human eye,
Right.
but it just doesn't work when you try to run it.
So it's like that recipe that looks amazing in the cookbook,
Exactly.
but then you try it out and it's a burnt mess
Yeah, totally.
in your kitchen.
Yeah, and this near-miss problem is a huge roadblock on the path to fully autonomous programming, especially in fields like healthcare or aerospace, where even a tiny bug could have, disastrous consequences.
So how does SEI address this challenge? Like, what makes it different from these other AI coding systems?
Well, IZI tackles this by taking inspiration from how human developers actually work. So instead of having like one big AI brain,
Yeah.
it uses a team of 5 specialized AI agents that mimic the different stages of the human coding process.
Okay, that's interesting.
Yeah.
So tell me more about these AI agents. Like, what are their roles?
So think of it like an assembly line for code.
Okay.
Okay, so you start with the synthesize agent.
So synthesize you.
Yeah, this agent takes a description of what the code should do,
Okay.
along with some examples of, inputs and outputs, and it generates an initial draft of the code.
So it's kind of like giving a human programmer a set of requirements and some sample data to work with.
Precisely, but here's where the real magic happens. The execute agent steps in
The execute agent.
and actually runs that draft code,
Okay.
tests it out, sees if it works as expected, and if it doesn't, it collects all the errors.
Gotcha. So this agent's like the quality assurance tester,
Exactly.
making sure the code actually does what it's supposed to do.
You got it. And
Yeah.
if there are errors, the execute agent passes them on to the instruct agent,
Instruct agent.
which acts like a code reviewer.
Great.
This agent takes those cryptic error messages
Yeah.
and translates them into plain English summaries that even non-programmers can understand.
Wait, so this AI agent can understand and explain complex coding errors
Yes,
in simple terms.
that's the goal.
It's pretty impressive.
It is. And these plain English bug summaries are then passed to the debug agent,
Debug agent.
which uses them to try and fix the original code.
So the debug agent is like the seasoned programmer who can just look at those cryptic messages and be like, I know it's wrong.
Exactly.
Yeah.
And finally, we have the rank agent.
The rank agent.
This acts like a judge. It looks at all the different versions of the code that the debug agent has produced
Okay.
and ranks them based on how well they fix the original errors.
Okay.
The best versions are then sent back to the synthesize agent for further refinement.
And the cycle begins anew.
Exactly.
Wow. So it's like this continuous loop of writing, testing, debugging, and refining,
Yeah.
all done by AI.
Mhm.
Now, you mentioned that these agents are powered by some pretty powerful language models.
Yes.
Can you tell me more about that?
Yeah, so they experimented with several large language models, including the well-known GPT 3.5.
GPT 3.5, yeah.
But what's really interesting is that they also used the open source Llama 3 model,
Llama 3.
which is significantly smaller than GPT 3.5.
Now, you might be wondering, why include a smaller model like Llama 3?
Yeah.
Well, one of the big questions in AI research is whether you really need these massive models for complex tasks like code generation.
Right. Right.
Could a smaller, more efficient model achieve similar results?
That's right.
And that's what they wanted to find out with this.
Exactly.
Now, before we move on, there's one more fascinating element to ASTI that we need to touch on,
Okay.
and that's the repair-replace dilemma.
Oh, the repair-replace dilemma. I like that.
Yeah.
Sounds very interesting.
Okay, so we'll get into that after the break.
Yeah.
All right, so we left off with this repair-replace dilemma.
Yes.
It sounds like CFighter has to make some tough decisions about, when to fix existing code and when to just start over. Can you explain that a bit more?
Yeah, so it's a crucial part of the process. You see, CIDR needs a way to navigate through all the possible solutions, right? Imagine you're searching for something in a maze.
Okay.
You could try every single path until you find the right one,
Yeah.
but that would take forever.
Yeah, you'd be exhausted.
Right. So you might decide to only explore a few promising paths at a time,
Yeah.
kind of like narrowing your focus. And that's essentially what CIDR does. It uses a technique called beam search to limit the number of code variations it explores at each step.
Okay, I think I'm starting to get it. So a narrow beam means that CIDR is focusing on, repairing the existing code,
Uh-huh.
but a wider beam allows it to explore, more radical changes, even generating completely new code from scratch.
You got it.
Yeah.
And the researchers found that finding the right balance between repairing and replacing is key to CIDR's success. Sometimes stubbornly trying to fix buggy code just leads to a dead end, just like, getting stuck in a corner of that maze.
Makes sense. Sometimes it's better to just start over with a fresh perspective.
Right.
So how did Sunny actually perform? Was it able to write good code?
The results were impressive. They tested SIDR on a benchmark called PSB2, which is designed to be a more realistic test of code generation than some of the earlier benchmarks.
So it's not just solving toy problems, it's tackling challenges that real-world programmers might actually face.
Exactly. And on this benchmark, SAID, powered by these large language models, managed to outperform traditional methods like genetic programming, which is a significant achievement. But what's even more exciting is that it wasn't just about raw performance. They also discovered some fascinating things about how SIDA approaches debugging.
You mentioned earlier that the instruct agent can translate those cryptic error messages into plain English.
Right.
Did they explore different ways of doing that?
They did. They tested two main approaches. The first one, called instruct static, uses predefined templates to generate debugging instructions.
Yeah, okay.
Think of it like having a set of rules that say, if you see error X, then tell the debug agent to do Y.
So it's more like rule-based, straightforward approach.
Yes. And the second approach, called instruct LLM, relies on another language model, in this case GPT-3, to craft those debugging instructions.
Okay.
This is more like having a human code reviewer who can analyze the code and provide more tailored feedback.
That sounds a lot more sophisticated.
It is, but, both approaches had their strengths and weaknesses.
Yeah.
The rule-based approach was simpler to implement, but it wasn't always able to capture the nuances of the errors.
Mm-hmm.
The LLM-based approach was more adaptable, but sometimes produced instructions that were too vague for the debug agent to understand.
So it sounds like there's this trade-off between simplicity and flexibility,
Right.
which is a common theme in AI.
Yeah.
But what really stood out to me was the fact that these AI agents actually have to communicate with each other.
Yes. Communication is absolutely essential.
Right.
You can have the smartest AI agents in the world.
Yeah.
But if they can't effectively communicate and collaborate, the whole system just falls apart.
Yeah, it'd be chaos.
It's like having a team of human programmers that can't understand each other's code.
Right.
Or, explain their ideas clearly.
That'd be a nightmare.
Exactly. So how did the researchers ensure that the agents in SADR could communicate effectively? Well, they paid close attention to the way that the instruct agent summarized the bugs and generated those instructions for the debug agent. They found that even small changes in wording could dramatically affect the debug agent's ability to fix the code.
So it's not just about having intelligent agents.
Right.
It's about making sure they can speak the same language.
Precisely. And this focus on communication highlights something really important about CIDR's success. It's not just about fancy algorithms and powerful language models. It's also about this subtle art of collaboration, even amongst artificial agents.
Now, before we move on to the limitations of the study,
Yeah.
I have to ask about something that really caught my attention. You mentioned that they used both GPT 3.5
Yes.
and the smaller open source Llama 3 model.
Right.
How did those two compare?
That's a great question. As you might expect, GPT 3.5, being the larger model, generally outperformed Llama 3.
Okay.
It solved more problems and did so more quickly. But here's the surprising part. Llama 3 wasn't too far behind.
Really? That's fascinating.
Yeah.
It seems to challenge the assumption that, You always need the biggest, most powerful model to get good results.
It does, and this finding could have some interesting implications for the future of AI-powered coding.
Hmm.
It suggests that smaller, more efficient models, especially those that are open source and accessible to a wider community,
Well,
might be a viable path forward.
that's pretty exciting. It could democratize access to this technology
Right.
and make it available to more developers.
Okay, so we've talked about the strengths of SADAR, but I know there are also some limitations to this study.
Can you tell us more about those? Okay, so we've talked about the capabilities and the limitations of SER, but now let's shift gears a bit. What does all of this mean for the future of software development? What kind of impact could CTI have?
Yeah, that's a big question and, one that's sparking a lot of debate.
Yeah.
Some people see this fully autonomous programming as a threat,
Right.
a potential job killer.
Yeah.
Others see it as this opportunity to free up human developers from the more tedious parts of coding so that they can focus on higher level creativity and problem solving.
So it's like that classic fear of, robots taking over, but applied to the world of software.
Exactly. But I think it's more nuanced than that. It's unlikely that AI will completely replace human programmers anytime soon.
Okay.
I think instead we're going to see a shift in the types of skills that are most valuable.
So instead of writing code line by line, we might be more like architects,
Right.
designing the overall structure of the software and then kind of guiding the AI agents to implement it.
That's one possibility. Or maybe we'll become specialists in debugging and refining this AI-generated code,
Yeah.
making sure that it's high quality and safe and meets all the requirements.
It's like how the invention of the printing press didn't eliminate the need for writers.
Right.
It just kind of changed the way they worked and the skills they needed.
That's a great analogy. And this adaptation isn't just for individual developers. I think the entire software development industry might need to transform.
How so?
Well, our current processes, the tools we use, even how we educate new programmers, all of this might need to be reimagined in a world where AI can write code autonomously.
Yeah, it's kind of mind-boggling to think about all the potential ripple effects.
It is, but it's crucial that we start thinking about these things now while the technology is still developing. We need to be proactive in shaping this future rather than just reacting to it.
Yeah, absolutely. So to our listeners out there, what are your thoughts? What kind of software would you have AI build for you if it could code autonomously? And what do you think the future holds for human programmers in this new landscape? We'd love to hear your ideas.
And as always, keep diving deep into those fascinating corners of the tech world. Until next time.